Welcome, my friends. I'm so excited because in this video we get to talk about normal distribution probabilities. So previously we've talked about how to find the probabilities within 1, 2, or 3 standard deviations of the mean on a normal distribution using the empirical rule. But now in this video, with the help of the TI-84 calculator, we can find any probability on the normal distribution. So let's go ahead and get started. Before we talk about probabilities on the normal distribution, we have to talk in general about probabilities on continuous distributions. You may remember that the normal distribution is a continuous probability distribution, meaning whole numbers as well as any decimal, no matter how precise, are allowed. That leads to a slightly counterintuitive fact about continuous distributions. For any continuous distribution, including the normal distribution, there are an infinite number of possible outcomes, since we can choose any decimal no matter how precise. And therefore, there is no probability at an individual point. That means for any constant a, the probability that x is equal to a exactly is going to be 0. Now, hopefully you're familiar with this notation, but if not, I will briefly explain. The p out front with the open parentheses represents what we call a probability statement. And here, this is saying that the probability that our variable takes on the value of some constant a is equal to 0. Consider any continuous variable, such as the amount of time that you must wait for the bus. The amount of time that you must wait for the bus is a continuous variable because we can have both whole numbers as well as decimals. You could wait 5 minutes for the bus, or 4.5 minutes, or 4.7 minutes, or any other decimal number. But you can always be more precise with your question. So instead of saying the probability that you wait for 4 minutes, you could say, what is the probability you wait for 4.7 minutes? Or 4.73 minutes? Or 4.78 minutes? Or 4.7792 minutes? Or you could continue to get as precise as you want to. And really this amounts to an infinite number of possible outcomes, because really those decimals could go out as long as you want to take them. So therefore, since we say each point is just one point out of an infinite number of possible points, we say the probability that our variable takes on any of those individual values is going to be 0. Another way to think about this is if we are calculating probabilities on a normal distribution, we're really calculating the area under the curve between 2 points. But if you only have one point on your distribution, you can't really find an area. You really need 2 separate points to find an area, which is shown by this picture over here on the right. I could find the area between 2 separate numbers, such as between 2 and 3, and that would represent the probability of getting a value on a normal distribution between 2 and 3. But it wouldn't really make sense to find the area right at 2 or right at 3 if we plugged in 2 or 3 for a. We really need 2 separate points so that we can find an area on the distribution. So the probability that x is equal to any single value we say is equal to 0. This means that the probability that x is greater than some value is the same thing as the probability that x is greater than or equal to some value, since the equal to part is not really adding any probability. The same thing is true for less thans. The probability that x is less than some value is the same thing as the probability that x is less than or equal to some value on a continuous distribution. There are 2 normal distribution functions that we are going to end up using on the TI-84 calculator. To reach the menu of functions, press the second key and then the vars key. I'll go to the calculator in just a minute to show you how this is done. The first function we will be using is what is called normal CDF. The inputs into this function are the lower bound, the upper bound, and 0 and 1. This will calculate the probability on the standard normal distribution if you enter 0 and 1 for the last 2 arguments. The 0 is referring to the mean of the standard normal or z distribution, which is 0, and the 1 is referring to the standard deviation, which is 1. Sometimes you might need to represent infinity or negative infinity as your lower or upper bound. We'll look at examples later. But if you need to represent negative infinity, you should be using negative 1000, and if you need to represent positive infinity, you should use positive 1000. The next function we will use is what is called inverse norm. The inputs into this function are some area to the left, 0 and 1. This will calculate the z-score corresponding to the specified area to the left on the standard normal or z distribution, as long as you enter 0 and 1 as the last 2 arguments. Let's look at a few examples. Let's say we want to find the probability that we sample a z-score between negative 1.5 and 1. This is sort of like asking, what is the chance that we sample a value from a normal distribution that is between 1.5 standard deviations below the mean all the way up to 1 standard deviation above the mean? The best way to visualize this is to draw a picture. We know that on the standard normal z distribution, we have 0 right down the middle. Negative 1.5 is somewhere to the left, and 1 is somewhere to the right. We are trying to find the area between negative 1.5 and 1, which represents the probability of sampling a value between negative 1.5 and 1. To solve for this, we can use a function on the TI-84 calculator called normal CDF. Let's grab our TI-84 calculator. We can press the second key and then the distribution key to reach the menu of functions. The normal CDF function is the second option down. Scroll down and press enter. For the lower bound, we will put negative 1.5, but make sure you put the negative sign and not the subtraction sign, otherwise you'll get an error. So we have negative 1.5 as our lower bound, and then for our upper bound we have 1. You should always leave the last two arguments as 0 and 1 if you're a student in my class. It is possible to sometimes change these last two arguments, but I think it's simpler to always leave these two as 0 and 1. Basically what that means is every time that you use the normal CDF function, you know that you're using z-scores, which have a mean of 0 and a standard deviation of 1. If you go down to paste and press enter, you will get the way that the inputs will look on a TI-83 calculator or maybe an older TI-84. In that case, you should be entering the values separated by commas, and the commas are right above the 7. Once you press enter, you will get the answer, which in this case comes to about 0.7745. The probability of sampling a value between 1.5 standard deviations below the mean, all the way up to 1 standard deviation above the mean, is about 77.45%. This seems logical because we know, based on the empirical rule, that if this number was negative 1 and this number was positive 1, then the answer should be about 68%. So it seems logical that this number would be a little bit larger than that. This probability is also the area between negative 1.5 and 1 on the normal distribution. Let's try another problem. Let's say we are asked for the probability that we sample a z-score that is greater than 2.2. This is the same thing as asking what is the probability that we sample a value on a normal distribution and it is more than 2.2 standard deviations above the mean. Z-scores represent standard deviations from the mean, so this is just asking what is the chance that we sample a value that is more than 2.2 standard deviations above the mean. Drawing the picture of the z distribution, we know that we have 0 right down the middle and 2.2 somewhere to the right. We are asked for the probability that we get a z-score that is greater than 2.2, so that's the area to the right of 2.2. We can solve this again using normal CDF, so let's grab our calculator. We can press second, distribution, and then scroll down to option 2. Press enter and we can enter in the values. In this case, the lower bound is asking what is the lower bound of our shaded region, or in other words, where does the shaded region start? Well, the starting point of the shaded region is 2.2, so we're going to put in 2.2 as our lower bound. The upper bound, on the other hand, is asking where does the shaded region end? But in this case, there really is no ending point for the shaded region. It really just continues to go in the rightward direction forever. So this is the case where we have to use 1000 to represent infinity. So we're going to put in 1000 as our upper bound. Anytime you have a greater than probability, you're going to have the upper bound as 1000, and if you had a less than probability, you would end up having negative 1000 as your lower bound. Once again, keep mu and sigma as 0 and 1, go ahead and paste, press enter, and you will get the answer of about 0.0139. The probability of getting a value that is more than 2.2 standard deviations above the mean is about 1.39%, which also represents this area on the normal distribution. Let's try a less than probability. What is the probability of sampling a z-score that is less than negative 1.3? Remember, z-scores represent the number of standard deviations you are from the mean. So this is the same thing as saying, what is the probability of sampling a value that is less than 1.3 standard deviations below the mean? Once again, we can go ahead and draw our picture. We have 0 in the middle and negative 1.3 somewhere to the left. We are asked for the probability that z is less than negative 1.3. So that's this area to the left of negative 1.3. Once again, we can use the normal CDF function to find the answer. So let's grab our calculator. We can go to second, distribution, option 2 for normal CDF, and then we can put in the lower and upper bounds. In this case, the lower bound is asking us, where does the shaded region start? But there really is no starting point for the shaded region. It goes forever in the negative direction. So this is the case where we use negative 1000 as the lower bound. I can't stress this enough. Anytime you have a greater than probability, you will have the upper bound as 1000. And anytime you have a less than probability, you will have the lower bound as negative 1000. The upper bound in this case says, where does the shaded region stop on the right-hand side? Well, the shaded region stops at negative 1.3. So I'm going to put an upper bound of negative 1.3. And then I can leave mu and sigma at 0 and 1. Go ahead and paste. And then I'll get the answer of 0.0968. The probability of sampling a value that is less than 1.3 standard deviations below the mean is about 9.68%. Now, so far, we've been using normal CDF along with z-scores to calculate probabilities. But what if we want to go backwards? What if we already have a probability and we want to find a z-score from the probability? Well, that's what the function called inverse norm will help us find. Let's look at some examples. Let's say we are asked to find the z-score such that the probability to the left on the normal distribution is 0.1. Once again, the picture is going to be your friend on these types of problems. We are asked to find the z-score such that we have 10% of the normal probability to the left. The way that we solve these types of problems where we already have an area or probability and are trying to find a z-score is using what's called the inverse norm function. On the calculator, press the second key and then the distribution key. Scroll down to the third option of inverse norm and press enter. By area, they mean the area to the left of the z-score on the normal distribution. The area to the left is 0.1, so we can put in 0.1. Now, on some TI-84 calculators, you might get an additional option for area to the left, area to the right, or area in the center. And if that's the case, then you should choose the area to the left to match what I'm doing here. Always leave mu and sigma at 0 and 1 so that you are telling the calculator you're using z-scores on the standard normal distribution. Go ahead and paste and press enter, and you will get the z-score, which in this case ends up being negative 1.28 approximately. The z-score such that we have 10% of the area on the normal distribution to the left is negative 1.28. Now, the main thing to watch out for with these inverse norm problems is sometimes the problem description will not give you the area to the left. You might instead be given the area to the right. But we know since the entire distribution must add up to 1 or 100%, if we know the area to the right, we can always solve for the area to the left. Let's look at an example. Let's say that we are asked to find the z-score such that the probability to the right on the normal distribution is 0.15. Well, here's the picture. We have some z-score towards the right-hand side, and the probability that we have a value to the right of that z-score is 0.15. Now, the inverse norm function takes the area to the left as the first input. If the area to the right is 0.15, that means that the area to the left must be 0.85, such that 0.85 plus 0.15 is equal to 1. Now we can go to our calculator to find the answer. So let's grab our calculator and press the second key, then the distribution key, and then we can go down to inverse norm. Next, we can put in the area, which in this case is going to be the area to the left, which is that 0.85. Once again, leave mu and sigma as 0 and 1. Go ahead and paste and press enter, and you will get the z-score, which in this case turns out to be about 1.04. The z-score such that the probability to the right on the normal distribution is 0.15 would be a z-score of 1.04. All right, here are a few problems for you to try. You are asked to calculate the following probabilities or z-scores using normal CDF or inverse norm. Draw the normal distribution to help you. So the first two problems, you'll be using normal CDF to find the probability, and for the last two, you'll be using inverse norm to find the z-score. Now recall that you need the area to the left for the inverse norm problems. So if you are given the area to the right, you're going to have to find the complement of the value that is given to plug into inverse norm. So just keep that in mind. All right, so hopefully you've had a chance to give these problems a try. Now, in most cases, you're not going to be dealing with problems that relate directly to z-scores. In most cases, you will deal with some other variable, whether or not it be weight or height or GPA or something else along those lines. And so I'm going to talk a little bit about how those problems will be structured and how you can solve those types of problems. Now, I've labeled these different problems with numbers. These are not numbers that you're going to see in textbooks, but this is just kind of a way for me to organize the different types of problems you can be asked related to a normal distribution. And the first one I'm going to call problem type number 1 is when you are taking some value on the distribution, we'll call that x, and you're converting that in some way to a probability. So an example of this might be, let's say I choose a random student and I want to know the probability that they score, let's say, higher than a 90 on the test, right? This would be taking an x value, which would be the score, and converting that to a probability in some way. And I've listed out a number of steps that you should take to solve this type of problem. So the very first step that I would advise you do is write out a probability statement to kind of describe what you are about to calculate the probability for. And that will take on the form of something like this. So maybe something like the chance that your variable is greater than some value, maybe less than some value, or in this case, this would be between two different values. This says, what's the chance that our variable is somewhere between 57 and 73? So step number 1, write out a probability statement that kind of describes what you're about to calculate. Step 2, you should convert that value into a z-score using the z-score formula that we talked about before. So basically take whatever that value was, or if there were two values, you would do it twice, subtract the mean of that variable, and then divide by the standard deviation. And that will basically convert that value into a z-score, how many standard deviations it is away from the mean. Then I advise that you write another probability statement, now this time in terms of z. The first one was in terms of x, which would be your variable that you're dealing with. Now z is in terms of standard deviations from the mean based on this formula that we've just done. So for example, let's say that you plugged 35 into this formula and you got 2 out. So then kind of the new probability statement would be, well, not x anymore, but the probability that z is greater than, now we have 2, because 2 would be what you would have gotten out of this formula. Or maybe for this type of probability statement where you have two different numbers, you run both of those two numbers through the formula, and then maybe you got -1 and 3. And then finally, once we have this form, we can solve the probability using normal CDF like we have been in the previous several examples. So once again, you may want to draw a picture to kind of help you know exactly what area to shade and what to put into normal CDF, but this is the last step that would solve the probability. So let's go ahead and take a look at a few examples. So we have Godzilla, and Godzilla, of course, he loves to destroy cities. That's what he's known for, and that's what he does. And, depending on the city, he does a different amount of damage. So the amount of property damage that he inflicts per city follows a normal distribution with a mean of $100 million and a standard deviation of $10. So we are asked, what is the probability that, for a given city, Godzilla inflicts more than $115 million of property damage? Now, at this stage, we've really only talked about the very first problem type number 1. So this is going to be the type of problem that we're solving. But in the future, we're going to introduce some other problem types, and it's always good to kind of take a step back and try to recognize what's being asked and why it fits into one form or another. So remember, I introduced problem type number 1 as you have a value for x, which in this case would be like a dollar value, and we're trying to convert that in some way into a probability. Is that what we have? Well, yes. If we look back at the example here, we have we're asked for the probability that he inflicts more than $115 million of damage. We do indeed have a value for x, that's be the $115 million, and we're trying to convert that in some way to a probability. So this does meet kind of the conditions for what I call the problem type number 1. So this problem gives us that our variable, which represents the property damage, follows a normal distribution, we use with a capital N here, and the mean is $100 million. I'm just going to use 100 and a standard deviation of 10. And we are asked to find a probability related to a value on this distribution, so this is going to be a problem type number 1. The first step of the problem is to write out a probability statement based on the probability that was asked. And in this case, they asked for the probability that he inflicts more than $115 million of damage. So the way that we would write that is it's the probability that x is greater than 115. Now, at this stage, you could start to draw the picture. You don't necessarily have to at this step, but if you'd like to, you can start to draw the picture to kind of visualize what's going on. We have our variable, which we're representing by x. 100 is the mean, so that goes right down the middle. And then that means 115 would be somewhere to the right. And we want to find the probability we are greater than 115. So I've shaded the area to the right, and that's really the probability that we are trying to find. Okay, step 2 is to go ahead and find the z-score. So here's the z-score formula. The z-score tells us to take the x value from our probability statement, subtract the mean, and then divide by the standard deviation. So we have all those numbers, so we can just plug into that formula. The 115 is the number from our probability statement. The 100 is the mean, which we have right here as well as up here, and then the standard deviation is 15. So if you type this into your calculator, you should get 1.5 as your z-score. Really means that $115 million is 1.5 standard deviations above the mean for this variable. Now at this point, you can kind of add a second axis to your graph if you'd like to. So you can put the z-scores on there. So a z-score of 0, we know always goes right down the middle of the normal distribution, kind of is represented by the mean. And the 1.5 is kind of corresponding to that 115 value, right? So those kind of pair up together. Many times I might not draw the x values on the picture, because when we go to the calculator, all we really need is the z-scores. But so we can kind of see this in the early examples, maybe I'll write both of those up there, have the x's and the z's on the distribution. So now once we have the z on the distribution, we can really see that the probability x is greater than 115 is the same thing as the probability that z is greater than 1.5. So we can also kind of write the probability statement in that way, and that's our step number 3. Finally, step number 4 is we can go to our calculator and use normal CDF to find the probability. So if I went and grabbed my calculator, which is right here, you may remember normal CDF is under the second distribution menu. And that's the very second option here, so normal CDF. Remember, we're always putting in the z-scores here. Some people can sometimes confuse this and do it with the x's. I highly advise that you do it with the z's. It is possible, but you have to, it's going to be a lot cleaner for us later if we just get in the habit of always doing this with the z-scores, especially when we get to hypothesis tests. So we're going to do the z-scores in here. We're going to put 1.5 as our lower bound. That's when the shaded region starts in terms of z. The upper bound is going to be 1,000 because we don't really have an upper bound. It goes forever in the upward direction. Or in general, you can remember anytime you have a greater than probability, your upper bound is going to be 1,000. We're going to leave mu and sigma at 0 and 1 because these are the mean and standard deviation of the z distribution. We can go ahead and paste, press enter, and we'll get our answer, which is about 0.0668, it looks like. So really what that tells us is that there's about a 6.68% chance that on any random city, Godzilla is going to inflict more than $115 million of property damage. And that completes this problem type number 1. All right, so let's go ahead and try another problem. We have the exact same information here, but the question here at the end is a little bit different. It asks, what's the probability that for a given city, Godzilla inflicts $88 to $110 million of damage? So just like last time, we have the same exact kind of given information. It's still following a normal distribution with a mean of 100 and standard deviation of 10. And if you read this here, once again, they're asking the same type of question. They're asking about a probability related to values of x, which in this case, x is representing our kind of dollars of damage, right? So again, just like last time, it's going to be a problem type number 1, where we're going from x to probability. The main difference with this one is we are asked to find basically a probability between two different values. So what that's going to mean is in our second step, we're going to actually have to find two different z-scores. So step 1 is going to be to, once again, set up our probability statement. This one's a little bit trickier because we have the two different values, but you may remember the way that you write that your variable is between two values is you list your smaller value on the left, your larger value on the right, your variable in the middle, which is x in this case, and then you kind of separate it with the less than signs. So we call this like a compound inequality, which says, well, x is less than 110, but at the same time, x is bigger than 88. So altogether, it means that x is between 88 and 110. So we can go ahead and draw our picture now if we'd like to. So we have 100 in the middle, 88 is somewhere to the left, and 110 is a little bit to the right. And then the shaded region is going to be the probability that we are trying to solve for. So then we can go ahead and do step number 2, which is to find our z-score. But in this case, there's going to be two different z-scores, one for the 88 and one for the 110. So to find the first z-score, we're going to be plugging in the first x value, which is 88, into the formula. So 88 minus 100, which is the mean, divided by the standard deviation of 10. And that gives us negative 1.2. And we can do the same thing for the second z-score. We take 110, that's our second z-score, subtract 100, and then divide by 10. And if we do that, we should get 1. So really we could go ahead and just add our second axis just like we did last time. We could have the z's on there. So we have negative 1.2 as our lower z-score. and our upper z-score is 1. So we could write our step 3, which is really just the probability that, not 88, but and now the value that we got when we plugged 88 into this formula, negative 1.2, is less than z is less than 1, which was our second z-score, right? So hopefully you're kind of getting the hang of this. We really are just plugging in these numbers to the z-score formula and then replacing those in our new probability statement. And of course, don't forget to change the x to a z. And then we're ready to go ahead and use our normal CDF function. So we can go ahead and grab our calculator again, press second distribution, go to option 2 for normal CDF. And in this case, we're going to put in negative 1.2 for our lower bound. That's where the shaded region starts. Make sure you use the negative sign and not the subtraction. So negative 1.2. And then our upper is going to be the 1. And we can go ahead and paste. And we'll get 0.7263 as our answer, which is also the shaded region in the picture. So really what that means is that Godzilla inflicts somewhere between or I guess he inflicts between 88 and $110 million of damage on 72.63% of the cities that he visits. So if you just chose a random city, then there would be a 72.63% chance that the damage would be between those two numbers. All right, so here is a problem for you to try. So assume that the average speed of a pitcher's fastball is 96 miles an hour with a standard deviation of 1.8 miles an hour and follows a normal distribution. So here are a few different questions. Find the chance that the pitcher is throwing a fastball with a speed less than 92 miles an hour. And then also find the probability that this pitcher is throwing a fastball that is between 94 and 100 miles an hour. So this very well kind of parallels the problems that I just did. So if you're kind of struggling with this, go back and just rewatch that part of the video. And I'll be back in just a minute to kind of help you through parts of these. But please do give these a shot. But I'll be back in just a minute to work through some of the problems. Okay, I'm going to go ahead and work through the first part. So if you have not finished the first part, please, pause the video again and try that. But I'm going to go ahead and work through this one. So they tell us in the problem that the mean speed or the average speed is 96 miles an hour and the standard deviation is 1.8. So we can kind of represent that using this notation. Our variable, which is the speed of the fastball, follows a normal distribution, mean of 96 and standard deviation 1.8. Then we can go ahead and do step number 1, which is going to be to write out our probability statement. We want to find the chance that it's less than 92 miles an hour. So that's the chance that x is less than 92. On the picture, that's going to look something like this. I could also put the mean on there. Looks like I didn't, but the mean of 96 would be right down the middle. 92 would be somewhere to the left, and we're finding the probability that we are less than that. So step number 2 is going to be to find our z-score. So just plug into the z-score formula, and you should get negative 2.2 repeating, I think, but I've rounded that to 2 decimal places. Typically, that's what I would do. And I could also put that on our picture as well. So I could write out my step number 3, which is the probability statement in terms of z. So now instead of x being less than 92, I have z being less than negative 2.22. And then we can go ahead and go to our calculator and write out the normal CDF calculation, which is negative 1,000 all the way up to negative 2.22 with 0 and 1. Remember, we're going to use negative 1,000 as our lower bound anytime we have a less than. The way you can think about that is, where does the shaded region start? Well, it doesn't really have a starting spot, so we just kind of put a really small number in there. And so our answer, if we were to plug that into our calculator, would be about 0.0132. So I'm not going to go through the second one, but that's how you do the first one. The second one's going to be very similar, but now you have the 2 different values. So please go ahead and give that one a shot as well if you have not done so already. Okay, so the problems that we've done so far have all been what I've called the problem type number 1, right? But there is going to be another problem type that we need to be familiar with as well. And it's basically just kind of switching things around. In the problem type number 1, we had a value of x, and we were trying to find a probability from that, right? We had the pitcher's fastball, and we wanted to find the chance that he threw a fastball faster than this or slower than this or something like that. But maybe we want to go the other way around. Maybe we already have a probability or an area on the distribution, and we want to find a value for x. Well, that's going to be our problem type number 2, right? This would be like asking how fast would the fastball be such that 97% of the fastballs would be slower or something like that. I already have a percent, like a 97% or a probability, and I'm trying to go backwards and find the speed of the fastball. But let me just remind you, problem type 1, kind of summarizing this, you're asked to find a probability given a value for x, like we've been doing in the previous different problems. And here were the steps that we've been using in all those problems. But now in a problem type number 2, we're going to be going backwards, right? In this case, you're asked to find what we call a raw score. The X value is oftentimes described as a raw score, like a weight, a height, an exam score, fastball speed, something like that. And in this case, we already have a probability or an area on the distribution. And we're going to be going through examples of those on the next several slides. So the steps for these are going to be, well, the first thing you're going to want to do is basically find the z-score corresponding to that probability, right? So if they say 97% is lower than this fastball or something, then you're going to have to find the z-score kind of corresponding to that value, right? And we can do that using the inverse norm function on our calculator. And then from there, we can find the raw score using the raw score formula, which is really just kind of a manipulation of the z-score formula solved for x. Okay, so make sure you have these down in our notes because we're going to be using kind of these steps here for the problem type number 2. So let's go ahead and look at an example, once again related to Godzilla. So I'm not going to read through all the information. It's the same information as last time. We got a normal distribution with a mean of 100 and standard deviation of 10. And the question they're going to ask here looks like they say at 90% of cities, Godzilla inflicts at most how much property damage, right? So once again, we still have the same kind of a setup here in terms of the variable, but you should be able to recognize hopefully that this is kind of the reverse of what we've done before, right? We're actually asking for an amount of property damage, right? Which is a value for x, but we are given an area or a probability, right? We're given the 90%, right? So in the previous problems, we were always solving for that area, right? But now we're going backwards, right? So sometimes they call these the backwards or the inverse problems, right? So hopefully you're able to recognize this is going to be a problem type number 2. We're going from that probability to eventually get a value for x. So the first thing I would do is probably draw out the picture. And in this case, they say at 90% of cities, he inflicts at most how much damage. So that's going to be a value for x such that 90% of the time it's something lower. So this is a pretty high value for x, right? And the first thing you're going to want to do is you're going to use the inverse norm function on the calculator to basically find the z-score corresponding to that cutoff. So let's grab the calculator. So this is under second distribution again. And it's the third option down for inverse norm. And the area is going to be the area to the left of kind of this value that we're trying to find. And the area to the left is that 90%. So we're going to put 0.9. And we're always going to leave the mean and standard deviation at 0 and 1. And if we paste that, we see that the answer is about 1.28. So here is the inputs here, and the answer is about 1.28. So that's step number 1. Step number 2 is going to be to find the x value, or in this case, the property damage amount, using the raw score formula. And we can just plug the numbers in. We already have those numbers. We have the z-score, which is 1.28. We have the standard deviation of 10 and the mean of 100. And if we were to plug those numbers into our calculator, we would see we get about 112.8. So the units there are millions of dollars. So basically what that tells us is that at 90% of cities, Godzilla inflicts at most $112.8 million of property damage. And that would be the completion of the problem. So these ones are a little bit quicker. There's only 2 steps compared to 4. But they can be very tricky because you got to pay attention to where this area is. So another way this problem could have been worded is, Godzilla inflicts at most how much property damage, or I guess maybe you'd say, what amount of property damage is such that only 10% of the time Godzilla inflicts more. Well, if they say only 10% of the time he inflicts more, they're actually describing the right tail. But you still would be using the 90% in your calculator because you always have to worry about the area to the left. So kind of my point here is sometimes they're describing the area to the left, like in this problem, but in other cases they might be describing the area in the right, and then you'll have to use that complement idea, right? If they gave you the 10%, you'd actually still have to use the 90% in the function. All right, so here are some problems for you to try, once again, based on the fastball example. So the same kind of thing here. And then they have 2 different problems which look, very, very similar to each other. So please pause the video and try these 2 problems. And I'll be back in just a moment to work through the first part. But the second one I am not going to end up working through. I'm just going to work through the first one. Okay, so just like last time, we have the same kind of setup here in terms of the variables. The fastball has basically a mean of 96 and a standard deviation of 1.8 and follows a normal distribution. And the question they ask here is 70% of the fastballs are faster than what speed? Well, if 70% are faster, then this is actually a somewhat slow speed. Like most of the time, it's faster than this speed, right? So we're going to have a value of x such that the area to the right is this 70%, right? Which means actually the area to the left is going to be the 30%. And that's going to be important here because remember, when we use that inverse norm function, we're going to need the area to the left, right? So the area to the left here is going to be that 0.3, which is what we're going to want to put into the function. And if you enter that into inverse norm, you're going to get approximately negative 0.52. Okay, then we can go ahead and do our step number 2, which is finding the x value using the raw score formula. So we can go ahead and just plug into that. We have negative 0.52 times 1.8, which is our standard deviation, and then plus 96. And if you do that, you get approximately 95.06. So 70% of the pitcher's fastballs are faster than about 95.06 miles per hour. All right, I think that completes everything I wanted to talk about in this video. So we will continue in the next video with the central limit theorem.